all, and welcome to Physics with Pranav. In this video, we'll be looking at part 2 of chapter 6 and 7, which is energy stores and transfers and energy sources. I've just termed it energy as a whole. In part 1 of this series for chapter 6 and 7, we looked at the most commonly tested concepts from this chapter by looking at recent past papers, i.e. from 2020 to 2022, as well as all variants of both paper 2 and paper 4. We understood that the most commonly tested concepts are descriptions of the different energy transfers and efficiency in different scenarios. We had to describe and explain different energy sources. And we also had to do calculations on kinetic and potential energy, i.e. gravitational potential energy, as well as efficiency calculations related to energy. In part 1, we also looked at the different types of energy stores and transfers. We looked at some example scenarios where they occurred. And we also looked at different types of energy sources. We looked at some pros and cons of using those sources. We identified the different sources as either renewable or non-renewable, whether they were clean or were emitters of greenhouse gases or other types of pollutants like particulate matter, sulfur dioxide, nitrous oxides. And we also looked at whether there is a link between these different sources of energy and the sun. In part 2, we'll be looking at formulas for kinetic energy and gravitational potential energy because you will be expected to use it. We'll be looking at a scenario where an object is falling and there is a energy transformation happening where it goes from having a lot of gravitational potential energy to kinetic energy and how that changes. And we'll also be looking at how to calculate the efficiency for energy. If you want to check out part 1 of the series for chapter 6 and 7, I have linked it in my description below, so feel free to check it out. So in this video, we'll start off with the formulas for kinetic energy and gravitational potential energy. So I've got a screenshot here of an object. It has a mass m, and it is at a height h above the surface of the Earth. And at this particular point, it has a velocity of v meters per second. The kinetic energy of the object is essentially the energy that the object has due to its motion, or the energy that it needs to sustain its motion. So if you think about it, if you had two objects that are traveling at the same speed, but one object is heavier than the other, it probably requires more energy to sustain that speed. Likewise, if you had two objects of the same mass, but one of the objects had a greater velocity because it's quicker, then it will need a greater amount of energy once again to be able to sustain that higher speed. So it's clear that kinetic energy is proportional to mass and velocity. And the formula for kinetic energy tells us that the kinetic energy is directly proportional to the mass and to the square of the velocity of the object. So the formula for the kinetic energy of an object is half mv squared. And for this particular object, it will be half mv squared because it has a mass of m and it has a velocity of v. So that's the formula there. And the gravitational potential energy of the object is essentially the energy stored by the object due to its position from the surface of the Earth or another body that exerts a gravitational force. So we know from experience that if you're trying to lift a heavy mass to the same height as a lighter mass, you have to expend more energy. Likewise, if you have two similar masses, but you have to lift one mass to a greater height than the other one, then again, you will have to expend more energy. So essentially, we know that the potential energy that the object stores when it's being lifted up or loses when it's falling is proportional to the mass and to its height from the surface of the Earth. So the gravitational potential energy is equal to the mass multiplied by the gravitational acceleration or the field strength multiplied by height. So gravitational potential energy is then equal to mgh for this object. Obviously, the questions that you will be tested on will be for objects that are falling near the surface of the Earth, but the other thing that gravitational potential energy does depend on is the gravitational field strength. So if you are dropping an object of mass m at a height h from the surface of a body that exerts gravitation, but then you've got a scenario on Earth, a scenario on the Moon, and a scenario on Jupiter, you'll have different gravitational potential energies in each of those cases because the gravitational field strength is different on Earth, Moon, and Jupiter. So hopefully that makes sense. Next, we want to look at how to calculate the change in the kinetic and gravitational potential energy of an object. So here's an object where it's falling towards the surface of the Earth, and we have captured it at two different positions. So you've got position 1 and you've got position 2. At position 1, the body has a velocity of v1 meters per second and height of h1 meters from the surface of the Earth, or the ground, sorry. And then in position 2, it has a velocity v2 and a height h2. So we know from the formulas that we saw before that the kinetic energy of the object at 1 would be half mv1 squared. Its gravitational potential energy will be mgh1. And then at 2, its kinetic energy will be half mv2 squared, because at 2, its velocity is v2. Its gravitational potential energy will be mgh2 meters, or rather, yeah, so h2 meters, so yeah, so the whole thing will be mgh2. And essentially, if I wanted to calculate the change in kinetic energy, it's going to be 0.5 mv2 squared minus 0.5 mv1 squared, or rather half mv2 squared minus half mv1 squared. Because the half and the m remain constant, the mass of the body is not changing, the half is a constant anyway. It would just be half m multiplied by the square of the difference in the two velocities. I have just noticed here that I have put the square term out. Technically, in mathematical terms, that would be v2 squared plus v1 squared minus 2v2 v1. I just want to say that that is incorrect. It should be v2 squared minus v1 squared. So it's not going to be v2 minus v1 the whole squared. So that is a correction that needs to be made. So apologies for that. But hopefully it's clear. So it'll be 0.5 or half m v2 squared minus half m v1 squared. If you take the half m out, you would have v2 squared minus v1 squared. So it's going to be the square applied to each of these terms separately, but not to the whole thing. And the change in gravitational potential energy is, again, if you take it between 0.2 and 0.1, it's going to be mgh2 minus mgh1. Mg is, again, constant because g is constant near the surface of the Earth. So if I took the mg out, I would have h2 minus h1. So that would be the change in the gravitational potential energy. So that is generally for an object whose mass doesn't change, that is falling close to the surface of the Earth, so its value of g doesn't change. Essentially what you have is a simpler formula for calculating the change in kinetic energy and change in gravitational potential energy. Change in kinetic energy really is just the difference in the square of the velocities multiplied by half m. And change in gravitational potential energy is the difference in the height multiplied by mg. So the next thing that I want to look at is how we can use the conservation of energy to be able to find the total energy transformations from point 1 to point 3. So here we have a falling object again, and we've taken a screenshot of 3 different locations. At each of the locations, so at point 1, its height h1 is equal to h meters. So that's the highest point the object is from the surface. Its velocity is 0, so this is the point where the object is just about to be dropped. And then we have an intermediate point somewhere during its fall called point 2, where its height is h2, and its velocity v2 is v2 meters per second. And then we've got a third point where the object has hit the ground, so it's got no height, and its velocity v3 is equal to v meters per second. So that's its maximum velocity right before it strikes the ground. So if we looked at the total energy of the object at each of these different situations, and let's assume that we're not accounting for thermal energy gains or losses or any sound that comes when it hits the ground, and let's assume that there are no other energy losses or gains in the system, it's just purely a transformation between gravitational potential energy and kinetic energy. So total energy of the object at 1 would be the sum of its kinetic energy plus its gravitational potential energy. That's going to be half mv1 squared plus mgh1 based on the formulas that we've seen for kinetic energy and gravitational potential energy. Because v1 is equal to 0, there is no kinetic energy. So essentially, an object at rest has no kinetic energy. So the total energy at 1 is just going to be equal to its gravitational potential energy, which is going to be equal to mgh, because h1 has a height of h meters. So total energy at 1 is equal to mgh. If we look at 2, the total energy of the object at 2 is going to be essentially the kinetic energy and the gravitational potential energy again. So sometimes I use the term potential energy, but I just use it interchangeably with gravitational potential energy. That's what I mean. I don't mean, I suppose, elastic potential energy or any of the forms of potential energy. I'm just talking about gravitational potential energy in the scenario. So again, if we substituted the values for height and for velocity in this situation, we have a total energy of 2 at half m v2 squared plus mg h2. And again, the total energy of the object at 3 would again be equal to the sum of its kinetic energy at 3 plus its gravitational potential energy at 3, which is going to be half m v3 squared, which is also half mv squared because that's its final velocity or the velocity at v3. And then we have mgh3, which is the gravitational potential energy, but because h3 is 0, that value is going to be equal to 0. So the total energy at point 3 is attributed only to the kinetic energy, so it'll be half m v3 squared. So now we observe, like, the total energy of the system is conserved, so the total amount of energy it starts with has to be equal to the total amount of energy it ends with. And we know at the start the body didn't have any kinetic energy because it was, held at a point and then dropped, so it was at rest at the start. And towards the end, as it's about to strike the ground, it's got no gravitational potential energy, so it's only got kinetic energy there, which means that in scenarios where an object falls and you have to interchangeably use the kinetic and potential energies to be able to calculate any of these values. So you may be given the total gravitational potential energy at the start. You may be asked to calculate the velocity of the object as it strikes the ground. You just have to remind yourself that the total energy of the system is conserved. That is, unless if it's a closed system, which means no energy is going in or going out, then total energy at different points for the system has to remain the same. So if the total energy at the start is all due to gravitational potential energy, and the total energy at the end is all due to its kinetic energy, then its gravitational potential energy at the start, mgh, has to be equal to its final kinetic energy, which is half mv squared. And you will be expected to use this to be able to calculate a number of things. So one of the examples that I just mentioned is if you're given the gravitational potential energy at the start, or you're expected to calculate it because they've given you the height, they may ask you what would be the kinetic energy of the object just as it hits the ground, right? So essentially calculating V. Or they may tell you that an object has this final kinetic energy. Can you tell us the height from which it was released? So usually you might have to calculate either the height or the velocity, or sometimes it's just a matter of stating that, if they ask you, right, okay, what's the gravitational potential energy there? And they say that all of it gets converted to kinetic energy. So what is the kinetic energy as it's about to hit the ground? Then you have to say that the gravitational potential energy equals the kinetic energy, right? So this is just a play on the conservation of energy, which states that for a closed system, the total energy is conserved. So that's the key thing to remember. And you have to know that in such a scenario for a falling object, the total gravitational potential energy at the start equals the total final kinetic energy, that it has at the end. Next, we look at the concept of efficiency. So efficiency is just stating how much of the energy that I input do I receive as useful output, right? So we've got a scenario here where there is an input energy of 100 joules, so that is the unit of energy, joules, is being added to this object. And then we can see that, and we don't need to know yet what the form of input energy is. It could be electricity, it could be chemical energy, whatever it is, and we don't need to really care about what the wasted output energy is and what the useful output energy is. Usually the wasted output energy is heat and sound. But again, if you've got a speaker system, then the sound is not a wasted output. If you've got a heater, then the heat, the thermal energy is not a wasted output. So it really depends on the system, right? But ultimately, to demonstrate the concept of efficiency, all you need to remember is, in this case scenario, I'm putting in 100 joules of energy into this object. 10 of those joules is wasted. 90 of those joules is converted into something useful that I want. So the efficiency is going to be the useful output divided by the total input. So the useful output is 90 joules. The total input is 100 joules. So I've got an efficiency of 0.9. And if I want to get the percentage efficiency, if you want to get the percentage, you just have to multiply it by 100. So that gives me a percentage efficiency of 90%. So the reason I've got this little asterisk here is to say that I have used energies here, but then you could also be using power to be able to calculate efficiency. We'll see this in the next chapter. A lot of these concepts are typically used interchangeably, as I mentioned in my previous video, that you will have to use the concepts of work and power along with the concepts of energy. So yeah, these chapters will be quite closely integrated, but in this scenario, I've shown you how to calculate efficiency using energy. But that is essentially what I wanted to cover in part 2 of the series for chapter 6 and 7 on energy. I hope with both of these videos, you now have a solid foundation of everything that is commonly tested from this chapter in past paper questions. I will obviously be releasing videos as well about how to apply these to recent past paper questions, and I will put a link for those in my description too. Anyway, I hope you enjoyed this video. If you did, please share, like, and subscribe, and I will see you all in my next video. Thank you very much.